Hey there, science fans. Today, we're diving into the exciting world of electricity. It's all about energy and how it moves. Think of it like a water park with water slides. Our first stop, voltage. Voltage is like the height of the water slide. The higher the slide, the more potential energy the water has to zoom down. In electricity, voltage, represented by the letter V, is the electric potential difference. It's the push or force that makes those tiny charges, called electrons, want to move. A big difference in voltage means a stronger push for those electrons. This push is what makes electricity flow through wires and power up our gadgets. Pretty electrifying, right? Now let's imagine those electrons like tiny swimmers ready to race down the water slides of electrical circuits. But wait, they need a path, right? That's where conductors come in. Get ready to explore them in the next section. Hold on to your safety goggles because we're about to unravel the mysteries of conductors and insulators. Remember those electron swimmers? Conductors are like the water slides that allow them to zip through easily. Conductors, like copper wires, have loosely bound electrons. These electrons can easily jump from one atom to another, creating an electric current. It's like a chain reaction of tiny swimmers passing a beach ball. On the other hand, insulators are like pool floaties that block the flow. Materials like rubber or glass hold their electrons tightly. They resist the flow of electrons, making them perfect for protecting us from electric shocks. Conductors provide a clear path for electricity, while insulators stop it in its tracks. It's this delicate balance that makes our electrical world safe and functional. Hold your horses, electrons. Just like those water park obstacles, there's resistance in the world of electricity. Resistance, represented by the letter R, is like the friction that slows down the flow of electrons. Imagine a narrow section in a water slide. The water slows down as it squeezes through, right? Similarly, materials and components in an electrical circuit can resist the flow of electrons. This resistance is measured in ohms, symbolized by the Greek letter omega, ohmega. High resistance means a lot of friction, making it harder for the electrons to flow. Low resistance means less friction, allowing the electrons to zoom through more easily. Resistance is a crucial factor in controlling the flow of electricity. It's like the park ranger of our electrical circuits, making sure everything flows smoothly and safely. Remember those conductors and insulators? Well, each material has its own resistance personality, called resistivity. It's like a material's ID card for electrical resistance. Resistivity, represented by the Greek letter Rho, tells us how much a material resists the flow of electrons. Think of it as the material's natural resistance level. We can calculate resistivity using the formula Rho equals sign RAL, where R is resistance, A is the cross-sectional area of the material, and L is its length. It's like measuring the resistance of a standard-sized piece of that material. Low resistivity materials like copper are great conductors. High resistivity materials like rubber make excellent insulators. Resistivity helps us choose the right materials for different electrical applications. Section 5, Ohm's Law, the traffic control of circuits. Buckle up because we're about to unlock the golden rule of electrical circuits, Ohm's Law. This law connects voltage, current, and resistance in a simple equation, V equals IR. Think of it like this. Voltage is the pushing force, current is the flow of electrons, and resistance is the friction that slows them down. Ohm's law tells us that the stronger the push, or voltage, and the lower the friction or resistance, the faster the flow of electrons, or current. This law is like the traffic control system of electrical circuits, helping us understand and predict how electricity will behave. It's a fundamental principle that engineers and scientists use to design and analyze everything from tiny circuits in our phones to massive power grids. Section 6, Ohmic versus non-ohmic, following the rules or not. Remember Ohm's law, the traffic control of circuits? Well, some materials like to follow the rules while others like to break them. We're talking about ohmic and non-ohmic conductors. Ohmic conductors, like those well-behaved drivers, obey Ohm's law. Their resistance stays constant, even when the voltage or current changes. It's like driving at a steady speed, no matter how long the road is. Non-ohmic conductors, on the other hand, are the rebels of the electrical world. Their resistance changes with voltage or current. Think of it like driving a sports car. The faster you go, the more the wind resistance changes. Understanding the difference between ohmic and non-ohmic conductors is crucial for designing and analyzing different types of electrical circuits and devices. Section 7. Feeling the heat resistors at work. Ever noticed how your phone gets warm after playing a game? That's because those hard-working resistors are converting electrical energy into heat. It's like a mini electric heater inside your device. When electrons flow through a resistor, they bump into the atoms of the material. This collision creates friction, which generates heat. The higher the resistance, the more collisions, and the more heat is produced. This heating effect can be both useful and potentially problematic. We use resistors in toasters, hair dryers, and electric heaters to generate warmth. However, excessive heat can damage electronic components if not managed properly. Section 8. Power up, the energy of electricity. Get ready to power up your knowledge because we're diving into electrical power. Power, represented by the letter P, is the rate at which electrical energy is used or transferred. We can calculate electrical power using three fantastic formulas. P equals sine Ivor power P equals current I multiplied by voltage, V. It's like calculating the power of a waterfall by multiplying the amount of water flowing with the height of the fall. P equals sine I2R power P equals the square of the current I2 multiplied by resistance, R. This formula tells us that power increases rapidly with higher current or resistance. P equals sine V2R power P equals the square of the voltage, V2 divided by resistance, R. This formula highlights that power is inversely proportional to resistance. Lower resistance means higher power. Understanding electrical power is essential for designing efficient and safe electrical systems. From powering our homes to charging our devices, it's all about harnessing the energy of electricity effectively. Section 9. Teamwork. Resistors in series and parallel. Just like a team of athletes, resistors can work together in series or parallel to achieve different electrical goals. Let's explore these teamwork formations. Series resistors. Imagine resistors connected like a chain, one after the other. In a series circuit, the current flows through each resistor in a single path. The total resistance is the sum of individual resistances. Parallel resistors. Now, picture resistors connected like parallel bars, providing multiple paths for the current to flow. In a parallel circuit, the voltage across each resistor is the same. The total resistance is less than the smallest individual resistance. By combining resistors in series and parallel, we can create circuits with specific resistance values to control the flow of current and voltage. It's like having a toolbox of resistors to build custom electrical pathways.